recording. Okay. So these are the different band gaps that we're looking at different temperatures. So here we have the absolute zero. And then at moderate temperatures, what you're going to see here is that, remember our Fermi level. Is everybody okay with Fermi level? Okay, that's that energy level, the last one. That's your highest energy level that's occupied. Okay? It's essentially the same thing as saying HOMO in the previous ones, right? Highest occupied molecular orbital. And so what you're going to see here is when we have that Fermi level was actually the place where you would have your band gap existing, right? Now, the difference in terminology there comes a little bit important here. And that's that the Fermi level is, again, the highest occupied energy level, right? So that being the case, it could technically be something that's slightly higher than the HOMO for various different reasons, like it's energetically favorable to not be paired. Okay. And so you can actually move that Fermi level a little bit. Okay. You can do things to it. Now, what you're going to see happening though is when we're no energy, no thermal energy, you would expect all of your molecules to essentially be in their lowest energy states, right? And those would be your ground states. Okay. And so if we add energy to the system, this is going to cause electrons to boost up into higher energy states, right? And that's actually what you're seeing when like you use an oven, right? You put extra energy on those coils. What happens to the coils? They light up, don't they? Okay. And that's actually, everybody's seen an old filament bulb? No? Yeah, a little wire. That's called a filament. And so when you put energy on it, it heats up. That causes electrons to boost up in the higher energy levels, go back down, and that causes light, right? Okay. And so you're familiar with the concept, of course. And that's actually what we're going to see here is as we add thermal energy, those electrons are no longer going to be majority in the ground state. As we add more and more thermal energy, in fact, the majority will actually shift up to higher energy levels, right? Now, what is this going to do in terms of band gap? Well, band gap is the difference between that ground state, the highest occupied one, and the lowest unoccupied one, right? And so if we're no longer just existing in that ground state, lowest energy one, if we have a large population that's up higher energy, that's going to shrink our band gap, isn't it? Okay. And so that's actually what you're seeing right here. That's actually the same sort of relationship you're sort of seeing right here, right? And so what you'll see is as you heat, for example, a semiconductor, because you have a wonderful computer chip, but you didn't really buy a great fan for it. And so it heats up. It will actually start overlapping and getting closer and closer to behaviors of a conductor. Now, modern day computer chips have safety protocols to stop that from happening. Okay. And so what it would actually do is after it gets to about 100 degrees or 90 degrees, depending on the computer chip, it's going to actually just shut it down. It won't let you use it anymore. Okay. But if it would continue going, it would actually go to a conductor. It'd eventually pass enough amperage through there that it would actually just fry itself. Yeah. And so it just burn itself out. Right. And that's because it's actually getting more conductive as you heat it. Okay. It's no longer acting as a semiconductor at that point. By the way, when you cool things, you can actually go the reverse direction and turn things into insulators. Mm-hmm.
What is the difference between like a conductor and a semiconductor?
So a semiconductor has a moderate band gap, and what's going to happen is under certain conditions, it will conduct. Mm-hmm. So when your energy is lower than this band gap, it won't conduct. Right. And so let's say you're doing a calculation. That's what semiconductors are used for. What you would be doing is you'd be going, let's say that this semiconductor right here is a 4, okay? And so you'd be going 1 electron, 2 electron, 3 electron, 4 electron. We have enough energy now. We're going to jump the gap, okay? And it's essentially a way you can then tally, right? Yeah. So under certain conditions, you'll achieve that band gap separation, okay? Usually that has to do with the voltage. So you can match the voltage to the band gap. Does that make sense?
Yeah.
Yeah. I'm doing it as a very low computer analogy. It gets a little more complex than that, but more of a complexity of combining over and over rather than completely different thing. Insulators just have a large band gap. Yeah. And then conductors have an overlap. So there's no significant band gap at all. Okay. You don't have to put a certain voltage and they'll go. Okay. Okay. So right here, we actually see some different band gaps. So certain metalloids have a band gap that's extremely convenient for us, matches up with voltages that are easy to manage and will work well with electronics. Okay. And those substances are silicon, germanium. And their band gaps are 1.1 electron volts for silicon, germanium 0.74 electron volts. Interesting little factoid, germanium actually would be a better semiconductor in many ways. And that's why the Germans were trying to use that as their semiconductor of choice. But it's extremely hard to purify and it's just very problematic to work with. And so we ended up with silicon as our semiconductor of choice. And that's computers now and phones and all that. So we don't necessarily want the same band gap for every single purpose, though, right? That wouldn't give us the sort of nuance that we would expect out of something like a computer, right? And so what we do is we make different types of conductors by taking these substances and we put another substance in with it. And so this right here is an example of an intrinsic semiconductor. This would be like a silicon or germanium. They're intrinsically semiconductors. They have a moderate band gap here, okay, that you can then boost electrons through. You can enhance the properties of either. This is called doping, or a dopant is being added, okay? You can either put extra positive charges on or extra negative charges on. And you do that by putting an element that has extra electrons or less electrons, okay? So for example, this would be an N-type semiconductor. And this, where here, what we're doing is we're putting on, which one was this again? AS, yeah. Yep, AS. And so that has one extra electron. And so you end up with an extra electron in your molecular orbitals, right? That boosted up one energy level. And so that then shrinks your band gap. And so it's easier to overcome your band gap now. Okay. And so these then have a smaller band gap. Okay. And you can do the opposites. You could actually remove electrons, in which case you increase the number of acceptors down on the lower level, and that's going to increase your band gap. Okay. You do this by just putting a very small amount of that other substance in there, and that will modify your band gap by relatively small amounts. Note that in this case right here, for example, because we have extra acceptors, if we build up electrons on this side, it's going to take longer to build up electrons on there, right? And so we, instead of being maybe 4, we would need 8 electrons to build up now. Okay? We can also do the other process where we're moving electricity the other way through this. And so we can actually let it fall back down. And so some of these are combined to do stuff like that. And when you look at modern day electronics, they're combinations of P and N type semiconductors. Okay? In a fairly complex pattern. I'm not going to go fully into that because it's just so far beyond the purvey of this course. And I actually do not use that on a regular basis. I don't know how many computer chips you guys think I'm designing and manufacturing in my office there, but I'm gonna say it's infinitely less than Intel. Okay. I do not have that equipment, do I? Actually, modern semiconductors, there's probably no human on the planet that could actually go through the entirety of a semiconductor and say this is what this part does. They're so complex now that they're generational products. And they're partially AI with humans optimizing parts now. Yeah, extremely complex. Anyways, this is the basis that you use to do this. Okay, this is like the material science level. So some of the things that you may have noticed here is, yeah, maybe we could take something that's not an intrinsic semiconductor, but if we dope it correctly, what happens? Let's say we took something that's currently an insulator and then we doped it properly. We could shrink the band gap, making it a yes. And so that's most of the research that's been happening is they've been taking what are normally conductors, doping them, making semiconductors of those, and then taking things that are not normally conductors like diamond and doping them properly, and then they become semiconductors. Okay. And so like the next generation of chips are looking to be like a metal oxides, or they could be graphenes or diamond. Diamond is actually a real popular one because diamond has really great thermal properties. Yeah, and we could actually make three-dimensional lattices pretty easily. So it would solve a lot of problems. But okay, so this is actually some different diagrams of some different crystal structures. So right here, you actually see an octahedral hole in red here. This one's a body-centered of a face-centered cubic unit cell. And so you see here in the blues are face-centered, right? And then the hole would be body-centered. And everybody see it okay? And that's where you would put the other anion if this was two different anions, or the other type of particle if it was different particles, etc. Okay. This right here is your diagram of your tetrahedral hole. You can see that makes a tetrahedral around the hole right there, like a diamond or like a CH4, right? Okay. Everybody okay with those so far? Yeah, I'm probably not going to go further into that because I think you guys get the idea, right? Here you have a simple primitive with your holes. This is just the other thing laid out. Yeah, just shifted. Okay, so this right here is actually the crystal structure of halite. That's NaCl in its specific structuring. And so this is the face-centered cubic unit cell. The chlorides are the big ones. They're the blue ones right there. The sodiums are the red ones. And they actually occupy every hole here. And so that's that structure right there. Right? Right there. Okay. Okay. This is if you structure it in polyhedron view. And this would be from the perspective of those sodium cations right here. Okay. So if you structured it as polyhedrons, what you would see is this would be a blue, right? Right there. Then we have a blue going over here, right? And then down. Okay. And then you'd have one over here and one out towards us, right? And so that would be your polyhedron structures. Okay. And these polyhedron structures are quite nice because you can actually take them and use them with some rules from Linus Pauling, of course, because everything three-dimensional was done by Linus Pauling to some degree. Guy was just prolific. And so this right here, he's the one that said you need three-dimensional models. Okay. So this is your crystal structure for cadmium chloride. Remember, this would be a CD2 plus within a Cl2, right? So you have two chlorines for every CD. Okay. Everybody understands red is the cations, right? Blue is the anions. Now, again, keep in mind, you're only going to occupy half of your O holes with the cadmiums because you can't have the same number of cadmiums, right? You'd have a positively charged crystal then. Okay? And so you're only going to have half the number of CDs, right? Cadmiums. Okay, so if we do this as a polyhedron holes again, from that perspective of the cations, what you're going to see is you'd actually end up with edge-shared polyhedrons here. And that's because of the 2+ charge, actually. So if we look here, 1+ charge, point shared, right? 2+ charge, edge shared. Okay? And that actually helps you predict your crystal structures and how things will bind in crystals. So let's look at some crystal structures for a perovskite. BAT, I believe, 03. I can barely read my own thing. Any better up there? Not much. No. Okay, so this right here would be from the TI 4+ vantage point. Right there. This is the BA 2+ vantage point. And again, the circles here are the BA 2+s on each of these. The TI 4+ is these little crosses, and then the oxygen 2- is the dark filled in spaces. So this right here would be a semi 3-dimensional. If we were to look at this as layerings, what we would see is this is actually be our layerings for our B and A. So that's the A, B, and what we'd end up getting is an AbO3 layering. Okay. So this right here would actually be your octahedron structure, as you can see laid out. And good God, I can barely see anything. Again, this would be the TI 4+, excuse me, cations right here in the octahedrons. The holes right here would be the BA 2+ in the greens, right there. Okay. And they need to be further separated in this case because the BA 2+ are going to further separate them because they'll introduce positive charge between, right? Which is why they're pushed a bit further out than you would have normally expected. Okay, so these are going to be some common eutactic ionic solids. These are going to be based on your close packed structures. The AB here is going to represent your two different types of cations, and X is then going to be your anion. And so what you would do here is you'd look at your formula, and you'd see what your formula looks like. So for example, if it's just A and then your anion, that would be like your NaCl, like your halide, right? That we looked at just a bit ago. If we were to come down here, and let's say we looked at something with a CCP, and it had a AB and then 3 of the anions, okay? So our perovskite that we looked at just a bit ago. That would be BaTiO3, right? See how it matches this formula. Cation, cation, anion, 3 of them, okay? And that's going to be this structure right here. So perovskite. I don't know if there's anything. I don't know how much you guys actually know about minerals. Probably not a super tremendous amount. Like this is fluorite right here. Very common fluorescent mineral, and it has calcium fluoride, excuse me. And so it's AX2, right? 2 of the anion, 1 of the cation. Okay. Okay, so let's talk a bit about lattice enthalpies in the Born-Haber cycle. The difference being Born here. The Haber cycle, many of you probably remember from Gen Chem, right? Yeah. That being the what makes fertilizer over most of the world. Though maybe that will change. People are really up in arms about it lately. Despite the fact that it's why most people can exist. So Do you know what would happen if we stopped using nitrogen fertilizer right now? We can only support somewhere around 25 to 30% of the population. Yeah. So you would have to kill off about 6 billion people. Did you know that the Europe actually tried to get several countries to stop using the nitrogen cycle and convinced one to do it, and they caused widespread famine. But they are right that we need to actually like deal with it because people are overusing it, and we're having a buildup of nitrogen on farmlands. But cold turkey is not the way. I think people that put forth such ideas should have to volunteer to be the first people to die from it, right? Yeah. Okay. Anyway, sorry. Political. Um, so this is actually the Born-Haber cycle right here. It's just how things um, crystallize. It's the different processes through which they have to go through to form crystals. And it's always a cycle because it goes all the way around. Because, of course, you can break the crystals apart, right? And so the first sort of process where we have sodium and chlorine gas, sodium solid, chlorine gas, right? Whenever we react a solid with a gas or really anything, we have to separate them out, right? So the first process would be taking the sodium atoms and they have to break apart, okay? They don't normally all break apart once into a gas, poof, but that you do have to separate out each atom, right? And so the next part is going to be getting the correct numbers together. So we have to break the chlorine bond, don't we? Okay. So we have one sodium, one chloride. And so that's actually the bond dissociation energy. You may recognize that from organic chemistry. Okay. Notice you only have to do 1/2 because you only need one chlorine from that. So each cycle of this would be 1/2 of it, or one chlorine more. This right here is again this going to gas. So that's actually phase transition, right? It's a pretty good chunk of energy considering its phase transition because sodium does not exactly want to be gas, right? And so this right here is going to be your ionization energy. That's going to be pulling an electron off of that sodium, right? Because sodium has to go to positive, okay? Okay, so the next part here is going to be the electron association energy. And this is negative because it's going to be coming energy back out, right? So the chlorine wants that electron, and so it takes that on, and that's the electron affinity, right? Yeah. Which is that energy right there. Again, negative because it's refunding. And this finally is that the association energy, the ionic binding energy, if you will. Okay, this is actually the making the ionic bonds. Okay, this is just for one of them that you would calculate it. The sorts of things that this is going to depend on. Can we think of any of the things that would depend on? Mm-hmm. Oh yeah, those will all that will all change all of these. Yeah, yeah. Like all of these under standard conditions, right? Um, almost every single one would get changed a bit by higher pressures, lower pressures, different temperatures. Some of these won't change depending on temperature, but the biggest sort of concerns here for this one are going to be things like the sizes of these atoms, right? This is actually your crystal structure information. And that's why this one's actually going to be sort of the focus of this chapter, because it's actually your crystal. Okay. And charges, size of your atoms, that sort of thing. Okay, so this right here is your lattice enthalpies for some selected solids right here. This is actually the formula for that UO. That's that one right there. So U0. This is that entire amounts summed together. So if we went ahead and added everything else up together, what we would notice is that the remainder would actually be U sub 0. Okay? And again, that's that crystal lattice energy. Okay? That's the energy coming back out because it's more stable as a crystal lattice, right? Okay, so what we notice here is these are the U sub O's for some different ionic substances. These are very common ones. That's probably, okay, I'm going to be honest with you guys. If you just do the normal sort of chemistry in life, that's probably 90-something% of what you'll ever see. Or something very similar. Yeah. Yeah, honestly. But if you get more into material science stuff, you might see some other stuff. Okay. And so the formula you would use is this right here, U sub 0. Okay. And so it's going to involve the radius here. And then up here is going to be the charges. Okay. And this is, again, the radius here. Don't worry, I'll give you guys an actual example. Okay. I just want you to have that formula down, because we need to play. Make sure we actually understand. Okay. Okay. Good God, that did not work well. Okay. So we're going to go ahead and plug this in. Now, this is that 120,200 right there. This value right here that looks like the little V, okay, that's going to be 3 for the Na2 plus with 2 fluorides. Okay, notice that is 3 particles, right? And so it's 3 because it's the number of particles this would break up into. Okay? Or another way of saying that the number of particles you have to arrange in this crystal. Okay? And then it's the charges. So we have here an Na2 plus and a fluoride, which has a -1 charge. And so those are the charges. 2 plus, -1. And then R0 here is going to be the radius of the fluoride plus the radius of your metal ion. So you'll see that we take 133, which is the fluoride, plus the 72, which is the Na2 plus. We're using a Mg2 plus as the actual size because that's something that's analogous to Na2 plus because of the 2 plus charge. They won't be particularly different. And then over here, that same radius value that we got before is going to come down to here on the bottom here. Okay. Can everybody see what you plug in each place?
Where you come from?
Number of particles.
So, for example, we're doing
Na2, F2. So Na2 plus, so it'll be NaF2. Yeah. So your number of ions that are going to be involved in the structure. And then this is just the radii added together. Don't forget, by the way, when you do these formulas, they're always ions. So it's not uncommon for you to see NaF2, right? And then sometimes people get like Na, right? Radius of Na. You don't want the radius of Na, right? You want the radius of Na2+. Okay. So you'd plug those in. This is actually going to give you kilojoules per mole, and that's going to, again, give you that energy that's involved in making the crystal. Okay? It should typically be something negative, though it's possible to make crystal lattices that would not be negative, to be positive. But it'd be very surprising for them to actually make a crystal, right? Because notice here that typically this would be higher energy up to this point. It's the formation of the crystal that actually gives you that refund of energy and makes this exothermically favorable, right? Okay. And that has to do because you're shrinking entropy here, aren't you? Yeah. Good God. Wow, that did not turn. I need to use a lower screen resolution screen when I do this. Okay. So again, remember that the radius of an ion is not going to be the same as the radius of just the atom, right? If you have a positive charge on it, the radius will considerably shrink down, okay? If you have a negative charge on it, the radius is going to considerably increase, okay? And so some very common ones are listed right here. You can actually find tables all over the place. This would actually be the formula, by the way. So if you had the radius of 1, you can actually get a very good approximation by just plugging the radius of the positive over the radius of the negative equals the charge of the negative over the charge of the positive. Okay. That gives you a pretty good approximation. Your R0 is always your radius of your cation plus your radius of your anion for that previous formula. Mm-hmm. That's the R0, yeah. Oh. Okay, so damn. Okay, so this is Linus Pauling's rules to identify the type of crystal that you would have. I can't even read that on this screen. I'm sure you guys can't read it either. So what I'll do is please go over these next class period. Let me know if anything didn't make sense. Okay. And I'm going to have to figure out how I can blow these up better and still get equations and pictures that make sense. Yeah. Okay. So I've already given you the parts for those, by the way. It just sums up what I've talked about before into a set of rules so you can go one after the other. Okay. So try them out. Try the homework out with them. And next class period, let me know if you have any difficulties, okay? Or before next class period, either way. I'll try to get that better deal. Okay, so far, the crystals we've been talking about, right, have been perfect, okay? Notice they're always perfect symmetry, perfect patterns, beautiful, right? So wonderful. Is that the real world? No, absolutely not, right? And so real crystals have defects. Most crystals are going to have defects. It's actually very rare for you to get crystals that are perfect throughout the entire structure. So some of the different types of crystal defects that can be present, often you're going to get more than one type. Crystal defects are actually incredibly common, okay? In fact, that's how you identify a natural crystal versus lab-grown crystals, the number of defects. Guess which has more? Natural, of course, yeah. And actually, a lot of the gems and stuff that you may have appreciated and liked, it's the defects you're enjoying. It's not the perfection. Yeah. Perfect crystals look kind of like glass. Kind of boring, actually. So the Schottky defect is going to occur when one or more atoms in the crystal lattice are actually missing. So you're actually going to have a missing hole. For example, you could have NaCl. If you looked at your NaCl crystals in your table salt shaker, you're going to have about one missing ion for every 430,000 ions, and that would be at a temperature of 1,000 Kelvin. Okay, so in a fairly hot oven, you'd have one missing in every 430,000. Now notice that is a pretty low number, especially considering the heat, right? But you are going to have missings. Okay. Your crystal lattice of CRO, this is going to consist of about 8% vacancies. Remember, for the ionic solids, the charges always need to be balanced overall. Yeah, you may be unbalanced in a very small portion, but only a little bit, okay? Every unbalanced is going to provide energy, right? And so whenever you have an absence of, say, a sodium, you'd have an absence of a chloride somewhere, right? And you'd have to have a overall balanced structure for your charges. So whatever number of absent cations you have, you'd end up having the same number of anions, right? Or another way of saying that that's more succinct and more accurate is you'll have the same equivalency. Does everybody remember equivalency? No? It's the charge times the number. So if you have 10 charge worth of missing sodiums, 10 plus missing, then you need to have a 10 minus missing somewhere as well, right? Yeah. Okay. Okay, so there is some alternatives here. We can have a missing anion that's actually balanced by substituting an anion having a larger negative charge somewhere else in your lattice. This would maintain your overall charge neutrality. So for example, if we have a silver chloride lattice, we could have missing chlorides, and then you'd have a similarly sized sulfur 2 minus ion that would be involved. We'll actually see a Schottky illustration in just the next slide, but I want to go ahead and get the other ones quickly involved in here, okay? So sometimes electrons can actually end up trapped in one of the vacant sites. So you have normally you have vacant sites in these crystals. You can actually end up with an electron trapped in that, where it can no longer move to the other sides because it's too high energy. So the barrier is too high energy, but it's in the higher energy state. So it never actually gets to where it should be. Okay. You are actually doing that right now, being in the high energy state, never getting where you should be because the energy barrier is too high, aren't you? That's what the floor is doing for you. Okay. The lower energy state being the ground, right? Okay. So you can, this is very common when you have sodium chloride where the crystal is actually doped with some sodium metal in the crystal. And so, for example, the sodium atoms would become oxidized to form Na+, and an electron is then going to be removed from that. It'll actually fill a vacancy where there would have been a chloride minus ion. And this can sometimes actually result in an F center. Whenever the F center is actually present, the compound can absorb visible light, and it will actually give a very characteristically yellow color, the typical yellow color. And so you've actually maybe seen this before. This would be yellow sodium crystals, yellow sodium chloride crystals. Table salt that has a bit of a yellow tinge to it. Okay? And it's not super common, but it's common enough that you may have seen pictures. The F in the term actually comes from F-centered, from the word Farbe, which means color, actually, in German. So certain types of ionic solids, especially ones with transition metal oxides, are going to have charge balances that can be accomplished by forming non-stoichiometric compounds. For example, FeO is an ionic solid where we have alternating Fe2 plus and O2 minus ions. If we have a Schottky defect is present, so you have an F2 plus missing from the crystal lattice, we don't need another metal, right? We don't need another cation. We can actually use Fe3 plus. And so Fe3 plus can counter that charge missing somewhere else in the compound. So this is one of the reasons why the transition metals, especially the ones with multiple common charge states, oxidation states, they're easy to achieve, have a tendency to have shifts of crystal structures throughout it. Is because you can actually have the different charge states forming defects. And so defects are quite common in these cases. Again, this is because you can actually have the Fe3 plus oxidized a little bit more, And this is then going to give you a non-stoichiometric mineral or ionic compound. So what you would notice is that you'd actually end up with iron and then 0.95 irons. So you'd end up with iron and then 0.95 oxygens because the extra Fe3 pluses mean you don't actually need as many irons in there, right? To make up the charge. So the ionic radius of Fe3 plus is actually smaller than Fe2 plus. Keep that in mind. So this can occupy your smaller T holes in your FCC unit cells. They'll actually form their own grouping within your crystal lattice. These are actually called Koch structures or Koch clusters. Okay, so if you remember your Schottky defects, remember that? Where we're missing one of these. So we're missing a chloride right there, right? Can everybody see that okay? Yeah. So here we're missing the anion. Right there we're missing the cation, aren't we? And there we're missing the anion. And what's that? Yeah, we got a 2- charge, don't we? Yeah, so the 2- charge substituted in for one of the -1 charges. And so we missed cation, anion, those match. That's our charge match right there. And then the second one is being substituted in for an extra negative charge here. Okay. All right. So this is actually a Frankel defect where one of the smaller ions has been displaced by an interstitial site in your crystalline lattice. And so you can see here that we've actually displaced this pattern here over. See it okay? And it just gets stuck like that because, again, to move, we would have to break the crystal structure in that area. And so it's an energy barrier. It gets stuck in a higher energy state, and that's your crystal defect from then on. If you heated this up, you could actually what's called anneal it. So if you heat it up enough to overcome that energy barrier, but not so much that your higher energy states become the norm, become the higher population, you can actually allow this to reform and go back down. Okay? But keep in mind that when we're talking about minerals and most compounds on this planet, they don't get to perfectly anneal down to the lowest energy states. They get kind of a sudden drop off. They go from like high temperature lava and then spew out somewhere and hit water and get frozen in whatever state they happen, right? Okay. So this right here is actually the example of an edge dislocation. This typically is what you see in a metal. And so you can see here that we actually have two slightly different structures here. See that? And what's ended up happening is we've edge delocated, this here being your edge right here, the crystal structure. So these are closer packed together. These are packed further apart. Really, really, really common in metals. Like, has anybody ever seen Tamagana katanas? No? Really cool if you ever get a chance. Check it out. They're by purpose misaligned. And so what they've done is they've actually taken several different types of iron and they form the katana out of it. And they take a harder crystalline structure of iron, and that's the outside, and then a softer one to support it under that can bend more. And so it cuts really well because iron has very large hardness, and but it doesn't fracture as easy because you got softer material that's more flexible. Yeah, supporting it. And so they're purposefully doing this, which is pretty cool, considering it's like 1,000-something years that they started doing that. I'm sure they had no idea that's what they were doing. So again, this is your different mechanisms of ionic conduction and crystalline solids having defects. This would be your vacancy migration right here. And so you're going to move to form a new vacancy, and you're going to move into the previous vacancy. This one right here is going to be the interstitial migration, where you're going to move through to a new spot, but you'll form the same filled structure on the other side. And then this one right here is a concentrated interstitially mechanism. This is kind of like your atoms, your cations in this case, are dancing. Okay, so one moves into a position, and it's going to cause the other then to move into a new position. Okay, and so it's a little bit like pool, right? Mm-hmm. Yep, combination. Yeah, we are combining them. Okay, this you probably recognize from Gen Chem. We've wrapped all the way back around. Congratulations. All that work to come back to where you started. This is the crystalline solids classification scheme. And so if we come down, we have atomic solids. These are going to be atoms at the lattice points. We have molecular solids. These are going to be molecules at the lattice points. These are things like H2O, CO2, NH3, that sort of stuff, right? And so you have intermolecular forces that are forming your solids, right? Ice. This right here is going to be your ionic solids, and you're going to have an ions at your lattice points, of course. And so those were those examples we were looking at with like sodium chloride and lithium fluoride. This is actually one of the more used stuff because there's a lot of things you can do with that, right? Because there's just a lot of ions and a lot of minerals. Let's go ahead and look at our atomic solids. You notice I didn't give you examples yet because there's different types of atomic solids. Okay. And so you may have been wondering diamonds and silicon and all the stuff I really like, right? And so that is network covalent solids, i.e., you have covalent bonds that attach everything together. Okay. And so they're going to have nonmetal atoms that will be at your lattices, and they're actually going to be attached with covalent bonds. You're going to have metallic solids, and these are going to, of course, be metal atoms, of course, right? And they're going to have metallic bonds, which are kind of bonds, right? More like electrons holding things together. Okay. Some of them get more covalent-like. If you were to look at like iron, for example, it can start getting fairly covalent-like. Then you're going to have London dispersion forces. These typically happen in things like group 18 solids, so the noble gas atoms, if you form solids from them. And you typically see this on the lower part of the periodic table. And so like argon, krypton, xenon, you can actually form solids from them. And you'll see noble gas atoms that will occupy the spaces, the last parts. Pretty unusual, but there's several techniques that you'd actually use that do this. You can actually make matrices with these. They don't interact a lot with the stuff inside. And so you can get solids of other things that don't really interact with each other. Because the noble gases are quite inactive, right? So this right here is your different chemical forces and their distance dependence and their average strengths right here. So this would be your ionic bonds. And if we were to look at the distance dependent, it's going to depend on your charge on your atoms, right? And it's going to drop off with your distance as you separate. The average strength tends to be somewhere in the 300 to 600 kilojoules per mole to break those. If we look at a hydrogen bond, it's typically between 20 and 40 kilojoules per mole to break that. And these are the hydrogen bonding, hydrogen bonded to fluorine, oxygen, nitrogen, chlorine, right? And those are the typical hydrogen bonds that you'd see. This is actually very complex. There is not a even relatively simple formula that's going to work in most of these cases. Okay. There's too many things you can attach to this X that's going to change things. This is ion dipole interactions. And so we have a dipole. It could be a, H2O or something like water. And they're going to have a drop off the radius, of course. It's only going to depend on one charge here, and then it's going to depend on your dipole over here. And it drops off as a square function. And this is going to have average strength somewhere in the 10 to 20. Notice they're fairly similar to the hydrogen bonding. Keep in mind when you're talking about these ion dipole interactions, most dissolving does not involve one of these interactions. It involves like 6. Okay? You make hydrated shells around your ions, right? And so keep that in mind when you're looking at these numbers, that this is typically not one of these interactions that you're talking about when you're talking about dissolving something. Okay? It's like 6 on each ion, right? So once you times 12 these numbers, that starts making more sense, right? Okay. This is dipole-dipole interactions. The strength drops off. Ion induced dipole interactions. Everybody knows what induced dipole is? Okay. So a dipole that's temporary, right? This is a dipole-induced dipole then. And this is London dispersion, which is induced dipole, right? Okay. Now, these forces are very small individually, but they're easy to add up, right? So keep that in mind, that these lower energy forces, many of these lower energy forces are very easy to start adding up. For example, hydrogen bonding, your typical sugar has like 5 or 6 of these, right? Yeah. And once you start looking at large hydrocarbons, see 30, well, you got 30 of these induced dipole London dispersion forces, right? By the way, I ran into a chemistry book that calls them London forces. Just London. No dispersion. Forgot the dispersion. Okay. Never seen that before in my life. So this right here is a molecular solid, and that's graphene. And does anybody know where the graphene is? You got it. You got it. It's your pencil, right? And so why does it work well as a pencil? Because you're shaving off layers, aren't you? And then depositing them on the paper. And then we use eraser, you scratch them off gently, hopefully only removing this part. All right. This right here is actually going to be like a mercury bromide. And you can see it layers out nicely into a molecular sort of style solid. This right here is your hard sphere models. So this is your Pauling rules up here. Notice that's going to be your ionic solids. Okay, so you have these hard spheres, and then they just associate together because they're attracted because of charge. Okay, and so ionic solids are going to be the stereotypical example of that. As you move away from this, you'll have it being less and less like that. Okay, and keep in mind what creates an ionic solid. Well, it's the change, the difference in those electronegativities, right? It's the difference in how well those hold on to electrons, right? And so something that has very large electronegativity differences makes ionic solids something. Okay. Okay. This right here is going to be your molecular solids, and that's going to be things that both hold on to electrons fairly well, right? Okay. And that's going to be, once you get the furthest along this, that's going to be your discrete covalent bonds. And then that's going to very heavily look like your valence orbitals, right? Your molecular orbital theory, okay? Because they're going to form covalent bonds. They're going to share them, maybe not perfectly equally, but still going to get shared, right? This right here is going to be your metals, and this is going to be things where you don't have high electronegativities on either of them. And so the electrons can move around fairly easily in that entire thing. They do have a tendency to have also d orbitals, which causes some of this. But this is really having to do with the fact that neither of them hold on to their electrons particularly well, so they can kind of be a little off from each other. Okay. Notice that you have alloys up here. All right. That pretty much wraps up everything. This is the band theory, by the way, that we finished on. That's where you're going to see your band theory. Because again, your orbital differences, your differences in energies are so low that they can skip up and down with even relatively small differences in thermal energy. So talking about them as being separate orbitals doesn't actually make sense, because your electrons are just going to skitter around in them all the time. Okay. This is actually a kind of neat example that I thought was kind of cool looking. This right here is your calcium chloride. As we go to CdCl2 and HgCl2, you can kind of see the difference here as you're going from something very ionic, right, over to more molecular. So you're shrinking that difference. And we're transitioning across one of these axes from ionic over to molecular. So that's actually this over here. Okay. I guess let me go ahead and start on the next chapter.